Introduction to computer control of processes. If you use any computing device in the process loop, then it is called the computer control of processes. Um, uh, for example, if you use PC itself as a controller that you are using in the lab, controlling fourth order process, what you are using is you are using the PC as PID controller. That is called computer controller process. Suppose you are using the same program in a microprocessor and you are using the microprocessor to control the loop, then it is also computer control of process. Or if you put all the program in a microcontroller and if you put it as a PID controller, then also it is called computer controller process. So embedded system that controls the loop is called computer control of process. Um, and today we are going to see computer control of process. This belongs to your fourth unit. Now, this is analog control system. In analog control system, what and all the components, what are the components in that control loop, SASO system? One controller will be there. For example, a PID controller. PID controller is the controller. Then a set point will be given to that controller. Then electro-pneumatic converter, because in that process, the final control element is a valve. So to operate that valve, we need a pneumatic signal. So this here, what we will get is 4 to 20 milliamps. Here we will get 4 to 20 milliamps. That 420 milliamps has to be converted into 3 to 15 psi. 3 to 15 psi. So that it can operate the final control element valve. So the manipulated variable manipulates the input to the process. Here, this is disturbance may enter into the process. A measurement sensor is here. That senses that is represented as a block diagram. The sensor is here. That senses. Then a transducer is there that transmits the signal to the controller. This is the analog control system. But anyhow, this process always analog. Process always analog. That's why we cannot convert the process into digital. So why it is called digital control system? The control system is digital. Whatever may be the element can be converted into digital system. If you convert these systems into digital, then it is called digital control system. But always the process is analog only. Process always analog. We cannot convert that into digital. Suppose a chemical CSTR is distillation column is. We cannot digitize that. That is always an analog system. So we have to control those analog system by using digital system. Then it is called digital control system. First, let us see what is the difference between digital signal and analog signal. Already you might have studied all these in signals and system as well as DSP. Once again, let us see. This is continuous signal. This is continuous signal. This is a discrete signal, not digital signal. There is a difference between continuous signal, analog signal, or continuous signal. Analog, continuous signal. Analog, continuous signal. Analog, continuous signal. This is analog discrete time signal. Discrete time signal, or we can say that discrete time signal, not digital signal. Discrete time signal, then it will be converted into digital signal. Discrete time signal, then it converted into digital signal. It has three phases. Analog signal is discretized, that is called discrete time signal, then it is converted into digital signal. How? First, this analog signal should be sampled, because why it should be sampled? Why it should be sampled? So to convert this into a digital value, discrete value, it should be sampled, because the ADC takes some time to convert that. During that time, it should not vary. Therefore, the sampler will sample that particular instant and retain that value till the conversion is over. That is called a sampler. So it samples and retains, samples and retains, samples and retains. So sampler. Sampler circuit will sample and retain. During that, the sampled value is called discrete time signal. For example, this varies from 1 volt to 5 volt. And then it decreases to again 1.2 volt. Like that, it decreases. So here, suppose here I sampled. Here I sampled. Then at this point, let it be 3 volt. So if I say at this point, that is when sampling period equal to 0, 1, 2, 3. When t sampling period equal to 3, the discrete value is 3 volt. Discrete value is 3 volt. The discrete value at this point is 4 volt. Discrete value at this point is 5 volt. Discrete value at this point is 2 volt. Discrete value at this point is 1 volt. Discrete value, 1.5, here 1. Discrete value at this point is 1 volt, like that. So if you sample and retain that value, then it is called discrete time signal. Then if you assign a code to that, then it is called digital signal. How you are going to assign code to that? Suppose I am using a 8-bit ADC, 8-bit ADC, 8-bit ADC I am using. Then what is the range of values for that ADC? 0 to 255. 255. Suppose I am using 10-bit ADC, then its value varies from 0 to 1023. 1023. Suppose I am using 4095. It varies if it is 12-bit. So it depends upon the maximum. Suppose its maximum value is 5 volt. The signal maximum value is 5 volt. Minimum value is 0. So this is converted by using a 8-bit ADC. Then in this case, 255 represents 5 volt. Suppose we used 10-bit ADC is used. In that case, 1023 represents 5 volt. Suppose we used 10-bit, 12-bit we used, means 4095 represents 4095 represents 5 volt. So that doesn't mean that 255 represents 5 volt. So it depends upon how many bit system we are using. If we use 8-bit system, then 255 represents 5 volt. So once it is converted into digital, it doesn't mean that this corresponds to analog value. It is a symbol used to represent the maximum value. This is that is called quantization. We quantized by using 8-bit, quantized by using 10-bit. Here the quantized by using 12-bit. So we are assigning some symbol, code. In other words, code to that values. That is called digital system. So now I think you understand the difference between continuous signal, discrete time signal, and a digital signal. Suppose you are having a digital signal. Another one more thing, one more thing I have to mention here. Suppose the ADC, 8-bit ADC, the reference signal given to the ADC is 5 volt. 5 volt. Then the maximum value of 255, this is reference given to ADC. Then 255 corresponds to 5 volt. Suppose the reference is 4 volt means, this 255 corresponds to 4 volt. If it is 10 volt is reference means, the 255 corresponds to 10 volt. That is also you should remember. Not only number of bits depends upon the what is the reference given to ADC. That is also there. That you should remember. Then how to convert discrete time signal into continuous time signal. So these are all digital signal. Then it is converted into discrete time signal. Discrete time signal. Digital signal is converted into discrete time signal. Once it is converted into discrete time signal, it can be converted into continuous time signal by using hold elements. Hold elements. It means if let it be the 1 volt. 1 volt E will be maintained till we get next sample. Then this 2 volt will be maintained till we get next value. This 3 volt will be maintained till we get next sample. Here next sample is again 0.9 volt will be maintained next. 0.8 will be like that. If you convert this can be converted into analog signal. This is step-like functions. How we can get very closer to analog value? The number of sampling points, if we increase, if you have intermediate values, many values are there. Here it is number of sampling periods. If you increase, you will get close to analog value. Not only that, you use number of bits also plays important role. Number of bits. If suppose you are using 8-bit data means, then it getting back again the same signal is very difficult. If you use number of bits increasing and the number of sampling period increased, both sampling period and bits both plays important role in getting back that original signal. That we will see now. One by one we'll see. So what is the importance of number of bits and sampling period? If you want to get back the in this way, you can analog signal is here. Whatever we are talking is analog signal, that is uh, discretized and digitized. It is transmitted from one end to another end. You are receiving my voice. Again it is a digital signal, that is discrete converted into discrete signal by using DAC. Then it is by using hold element, it is converted into continuous signal. So for that, this number of the sampling period as well as number of bits used is plays very important role, that we will see later. First let us see the sampling period. Sampling period is very very important. Here we are sampling the signal at the rate of 1 samples per second. So the sampler in the ADC sampler is there. It samples at the rate of at the rate of 1 second. So if you use yeah, hold circuit, what it will do? It will do like this. It will do. It will do like this. So if you increase the sampling period, definitely there will be improvement here. If you decrease the sampling period, what is the signal we are getting? If you do a zero order hold, this is the signal. There is no resemblance between this signal and this signal. And this is somewhat resembles to some extent, but this is not at all resembling, because very poor sampling period. Here sampling period is 3 seconds. Here sampling period is 1 second. If you increase the sampling period, getting back that original signal is not at all possible. Then how to here one more example. This is sampled at a particular sampling period. You are having 3 sampled values. It doesn't involve the maximum values are not at all involved. Minimum values also not involved. That's why it can be digitized. It fits to this as well as this is the actual signal as well as this. So if you get back that original signal by using these sample values, it like this one. It won't reflect this original signal. So sampling period is very important to get the complete characteristics of the signal to be transmitted. So sampling period plays an important role to retain the characteristics. Here, further it is sampling period is increased. We see that only five samples are there for this entire signal. What you are getting get back is this. There is no relation between these two. So sampling period plays very important role in getting back the original signal. For uh, for process control point of view, uh, what uh, what should be the sampling period? Because there also we are using the signal. It will be sampled and it will be sent to the controller. So at what rate it should be sampled? At least 0.1 time the time constant. Time constant is 3 seconds, means at least it should be sampled at the rate of um, 0.3 seconds. So each a duration of time constant means at least it must have 10 samples. Then that is sufficient. Or it should be 0.1 times dead time. If dead time is dominating than time constant, and dead time dominating systems, it should be 0.1 times dead time. So during the dead time, it should have at least 10 samples. That is the thumb rule used in process control. So generally, what is the rule to select the sampling period? That is Shannon's sampling theorem. In that, the sampling frequency is, so far we said sampling period. If you divide that sampling period per unit time, if you find unit time, number of samples per unit time, you find, then it is called sampling frequency. The sampling frequency must be at least at least at least twice the frequency of the signal to be sampled. That is Shannon's sampling theorem. At least twice. Then this is to get back the original signal minimum. Minimum. This is minimum sampling frequency at which the signal to be sampled. Resolution means that bit I said. One is sampling period. We have seen sampling period. Then bit number of bits that related to resolution. That is related to resolution. Um, Suppose I'm using n bit ADC. In that, the resolution is 1 by 256 minus 1. That is equal to 1 by 255. 1 by 255. 1 by 255. It means there are 0 to 255 codes are available to represent a span of 0 to 5 volt. Let us assume that the signal range is 0 to 5 volt. To represent the sample of in the range 0 to 5 volt can be represented in 0 to 255 codes only. It means the difference between one code and another code is 1 by 255. 1 by 255. In other words, the input is 0 to 5. What is the input range? ADC 0 to 5 volt. What is the output range? 255 maximum. Minimum is 0. So 5 by 255. That is 0.039 volts. So if any value is less than the difference between Suppose one value is sampled. Therefore, let us take this example. Um, this is a signal increasing that is sampled between this point and this point. If between this point and this point, the value is less than, the difference is less than 0.039 volts, then it will give the same value for both samples, for this sample and this sample. That is the meaning. That is called resolution. So at T1 it is sampled, at T2 also it is sampled, but the difference is less than 0.039. 0.039 volts means for T1 it gives say it gives 200. The value at this point is 200. For T2 also it gives 200 only, because the difference, voltage difference between these 2 points is less than 0.039 volts. That is the smallest value that can be sensed by the ADC is resolution, or 0.78%. So the percentage 0.78, less than 1%, 0.78%, it's resolution. For example, instead of using 8-bit, suppose you are using 12-bit, means the smallest value that can be sensed by an ADC is 0.0024 volts. That is 0.05%. So its resolution is more. It is more sensitive to changes. So it can sense a voltage change of 0.00224. As a bit increases, resolution increases. As number of bits increases, resolution increases. Then sampling period means we are not continuously taking values. Suppose sampling period is 1 second, means in between there is no work for ADC. ADC will work at this point at 0 seconds. Then it will work only for at 1 second. Then it will work for 2 seconds. That's all. So it will be ideal. The ADC will be ideal in between samples. Suppose it can give its value within 30 milliseconds. 30 millisecond, between 1 second. So in 1 second, 30 millisecond, 10 power minus 3. Suppose in 1 second, here sampling period is 1 second. Cross control are large time constant process. That's why sampling every 1 second is sufficient. Depends upon the time constant. Already I said depends upon the process time constant. It should be 0.1 times time sampling period must be 0.1 times sampling period, or 0.1 times dead time. Already we have seen. In this case, let us assume that the 0.1 times time constant is 1 second. If it is sampled at 1 second, then how many times ADC can be converted? ADC can convert the signals 1 by 30, that is 0.03, 0.03 in multiplied by 10 power 3. So 30 times it can convert ADC in between 2 samples. That's why in ADC, multiplexer will be cascaded with that ADC. That is called channel 1, channel 2, channel 3. So it will convert first to this, then it will convert this, then it will convert this, then it will convert this. That is called channels. So in one ADC is sufficient to convert many signals if the sampling period is small. DAC is a reverse process. Already we have seen that process is analog. Once it is sampled, it can be converted into digital here. Similarly, here also digital, controller digital, everything digital. But after final control element, this must be analog. So here, somewhere here, it should be converted into analog signal to operate the valve. To operate the valve, you need analog 3 to 15 psi signal. So this digital output, here it is analog. If it is a digital controller, if it is digital input output, it should be converted to analog 3 to 15 psi to operate the valve. Anyhow, finally it should be a analog value. For that we need DAC, digital to analog converter. Are you hearing? Okay. DAC converts digital signal into analog signal. Digital signal into analog signal. 0 to 100% is the controller output. Controller output is 0 to 100%. If 100% is represented by 255, if it is 8-bit system, 0% is represented by 0. So the controller output varies from 0 to 255 if it is a 8-bit system. Suppose 50% is the controller output, means that is the controller output is 127. To convert this 127 into analog value, the analog output is 127. The reference voltage is 5. 127 multiplied by 5. Analog value is range is 0 to 5 volt. Let us assume. Digital is 8-bit, so 0 to 255. So 0 to 255 in digital corresponds to 0 to 5 in analog. So 127 multiplied by 5 divided by 255, that gives 2.49 volt. Almost 50% means 2.5 volt. 2.49 volt it gives. So that is the function of digital to analog converter. If it is in digital number, say 127, that will be converted again into analog signal to 2.49 volts. So what is an digital control system? Digital control system is already I told you that this is analog final controller, that is valve also analog. So this here we need 3 to 15 psi. Here we need 3 to 15 psi is required. Here here it is 4 to 20 milliamps. It is 4 to 20 milliamps. Then this 420 milliamps is coming here because the DAC gives 420 milliamps. Let us assume this 420 milliamps must be converted in R 0 to 5 volt. Let us take this way. Why 420 milliamps? Let it be 0 to 5 volt. That 0 to 5 volt should be converted into 3 to 15 psi to operate this final control element. So this 3 to 15 psi is given to this process to operate its final control element. So this part, from this part up to this part, it is analog. This is analog. In a digital control system, this is analog. But here, a measuring sensor is attached to this output. It is also analog. The transducer, again, it is analog. So this part also analog. So this is also analog. So we can say that if you draw a line To its right, everything is analog. To its left, there is a sampler that samples the analog signal coming from this transmitter. Say level process means it is a converted into digital signal by using AD converter. That is given to the controller, say PID controller. Let it be a PC or microcontroller or microprocessor, whatever it may be. It acts as a PID controller given to that. And it gives controller output. We are giving set point to that. Set point to that. Here, set point is given here. It gives a controller. So it's to its left. It is digital controller. But the PID controller that is available in the lab, already I told you that it is made up of microcontroller, but it looks like an analog controller. Its output is it looks like an analog controller because its output is 4 to 20 milliamps, and input also 4 to 20 milliamps. So as if it looks like analog device. Earlier, while op-amp based PID controllers used, it will be like that only. Output is 420 milliamps, input is 420 milliamps. So even though it is converted in digital controller, it appears like analog controller because the sampling is very high. Whatever may be the time constant of the process, whether it is thermal process, very large time constant, or flow process, the sampling period is very high. That's why it appears like continuous signal. That is the reason why. Suppose I am taking samples very close to that, like that I am taking samples are taken very close to that. Every 1 millisecond sample is taken. Let us assume if you join all these points, you will get again the same value. So the universal PID controller that is available in the market has very high sampling period. Sorry, very small sampling period, very high sampling frequency, very high sampling frequency. That's why it again there is inbuilt DAC and inbuilt ADC is there, so that you can directly connect analog voltage and you can take analog output. That's why it is nothing but an analog PID controller. So that we are applying all analog techniques to that because the sampling period is very high, so that we can apply all analog techniques to that while using that PID controller. Because sampling period is not very large, it is very small, say 1 millisecond. That's why it can be used as if it is a analog PID controller. We may get confusion whether it is analog PID controller or digital. You can look it as a analog PID controller because of very high sampling frequency, both for ADC and DAC. You cannot distinguish. Suppose you are having analog controller means if you parallelly operate both controller, you are giving same error to both controller means you cannot distinguish the output between these two controllers. The true analog and as if analog both will give the same output because of very high sampling frequency.